That is completely inaccurate. I am nowhere near that round. Also, my children are of varying sizes. Well, I mean, number 6 is the smallest one. That is true. But they are varying sizes. In any case, I'm offended. That's not true. I'm not offended. I actually think this is pretty great. All right, now let's learn a little bit more here about orbits. So most orbits aren't actually circular. Most natural orbits are going to be some sort of an ellipse. Now, before we get too far into example 6, which is what your notes packet should be on, we should probably review a couple of things about ellipses, okay? So in the previous video about Kepler's 3 laws of planetary motion, we had a picture that, you know, okay, fine, I drew an ellipse, I labeled the semi-major axis on it. There was one thing that I did not include in that video that I probably should have, that I will include right now. It's a super important geometry fact that you need to know in order to be able to work out most problems that involve elliptical orbits. And there's a bunch of different ways that they can slice it, but it's all going to come down to this geometric fact. So here it goes. We said this is called the perihelion distance, and over here this is the aphelion distance. So in an elliptical orbit, sometimes the planet or whatever it is close, sometimes it's really far away, or maybe only a little further away. Regardless, there's individual distances. So the perihelion distance you might call, say, R1. The aphelion distance you might call R2. Neither one of those values is by itself especially useful. Meaning if you just know the perihelion distance but you don't know the aphelion distance, you can't necessarily do a whole lot with that unless you have some other information like the period of the orbit or something. All right, now, if you know both distances, though, you can get the semi-major axis. All right, now, let's talk about why we need to know this distance. Let's say that they give you a question where they tell you the perihelion distance is number. The aphelion distance is bigger number. What is the orbital period of the planet, or whatever it is? Well, you might immediately go to Kepler's 3rd law, and you'd be right. That would be the place to go. It's a useful equation for this sort of thing. And so then you're looking at it and you're like, which R do I plug in? Do I plug in the perihelion distance? Do I plug in the aphelion distance for the A here? The answer is neither. Don't plug in either one. Neither one is actually the right thing. What you want is the semi-major axis. That's what determines the length of the period. Frankly, it doesn't matter what either of those two are. If you had an orbit that was, let's say, distorted from this a little bit, like it was, let's make it outrageous. Oh, this is hard to draw. All right, but there's our new orbit. If you look carefully, I tried to make that second ellipse I drew on top of this one be the same total length as the first one that I drew. Why is that important? Well, because if it's the same in terms of the major axis, then it has the same semi-major axis, and the semi-major axis is what determines the orbital period. So it doesn't actually matter how that ellipse is shifted around. What matters is what is half of the distance across that ellipse. That's what determines how long the orbital period is going to be. All right, so putting this together with what I wrote up here, the semi-major axis is halfway across, and that is A. The whole way across would be 2A. That means that if I take the perihelion distance plus the aphelion distance, that's the whole way across the ellipse, and so that must equal 2A. Useful geometry fact, because if I know both distances, then I should be able to solve for the semi-major axis. And then I can find the orbital period. We can also go the reverse of that whole process, which is actually exactly what example 6 is going to do, but you had to know that geometric fact in order to be able to do anything else in this question. All right, so now, example 6. Find it in your notes packet. It's all about Halley's Comet. So the first few parts of the question are really just geometry review, which we kind of review right here. So let's just skip straight to part D. D says, a common astronomical unit is the astronomical unit. Okay, that's great. And AU, 1 AU, it says 1 astronomical unit is approximately 1.5 times 10 to the 8th kilometers. Halley's Comet, at its closest, is 0.6 astronomical units away from the Sun. Okay. All right, oops. All right. At aphelion, it's some much larger distance away, right? It doesn't actually say what it is. And part D, all it wants us to do is turn that into kilometers. Okay, so that's a pretty simple operation, right? Just 0.6 times 1.5 times 10 to the 8th kilometers. We're going to get 9 times 10 to the 7th kilometers. All right, now just preemptively, let's go ahead and change that to meters because kilometers is not going to be useful. 9 times 10 to the 10th meters is our perihelion distance. All right, next thing. It says in part E that the orbital period of Halley's Comet is 76 years. So that's T equals 76 years. Okay, all right. Determine the aphelion distance. Okay, don't panic. What you should do at this point is think, well, okay, I know some geometry, and I know Kepler's third law. I should be able to put those together to solve for the aphelion distance, because I know R1, that's the perihelion distance. I can figure out the semi-major axis from Kepler's third law. If I know the semi-major axis, I can plug it in up here and solve for the aphelion distance. Okay, so this would be a great time to pause right now and see if you can do it, and then resume periodically for more hints. All right, hint number 1 if you're stuck already. I don't know why I said already, but all right. 76, just that's no good. You need that to be in seconds. All right, so let's see, 76 years. There's 365 days in a year. All right, we'll ignore the 0.25 for a leap year, whatever. 365. Okay, so multiply that by 365, and that will be the number of days. Times 24 will be the number of hours. Times 60 is minutes. Times 60 again will be the seconds. All right, so it's going to be a lot of seconds. All right, so make sure you're plugging in T in seconds. There it is. 2.397 times 10 to the 9th seconds. Don't forget to square it. All right, now, the M here. Sometimes people plug in the mass of the Earth. Halley's Comet does not orbit the Earth. It actually orbits the Sun. So this should be the mass of the Sun, which is about 9 times 10 to the 30th kilograms, I believe. Okay. Let's see. Sorry. How about, let's try 2. 2 times 10 to the 30th. I don't know where that came from. Okay. All right. Now, I've said this before. If you're having calculation troubles, take it slow. Figure out what g times m is. Write that number down. What's 4 times pi squared? Write that number down. Don't forget to square this and write down what that is. Okay, here we are again. So we've got 5.74 times 10 to the 18th. Woo, big number. All right, equals 4 pi squared. 39.48. Okay, g is 6.67 times 10 to the negative 11th. So we're going to have 1.334 times 10 to the 20th in the denominator. I hope I did that right because there's some mental math happening here. I know I'm using the calculator, but there's still some mental math. There we go. All right. Okay, and then if you're like thinking, well, shoot, how do I take a cube root? Sometimes people will say, you know, there's a special button under the math or whatever. Just do it to the 1/3 power, right? Exponent, parentheses, 1 divided by 3, close parentheses, enter. That's usually my preferred way of doing it. All right, so let's see if we can all calculate it together. Remember, it's important that you go through the exercise in your calculator. You need to try it in your calculator. Do that, okay? If you just see me do it and you're like, yeah, that makes sense, part of the goal here is for you to learn how to make your calculator do what you want. Otherwise, your calculator is your enemy, okay? There's a lot of places the calculations can go wrong. You have to have experience with typing it in and either getting it right or getting it wrong and figuring out what you did so you don't make that mistake twice. And we're nearly there. If you work it all out, you should come up with a cubed is this number. So that means a is this. All right, great. Now, if we then take all that, put it in here, 2 times this. All right, that's 5.37-ish times 10 to the 12th. That's our 2a. Equals R1 plus R2. As we learned over here, R1 is 9 times 10 to the 10th. So that means that R2 is 5.28 times 10 to the 10th. All right, well, that was what we wanted to know. Now, I want to talk next, before I close this video, a little bit about some of the stuff. Oh, there that is again. Some of the stuff you're going to see on the homework, which is going to relate to actually like some of the stuff that NASA does when they're trying to plan out a mission to like send something somewhere. Believe it or not, it doesn't work like this. All right, so Sun, Earth, Mars. If you want to get to Mars, here's the wrong way to do it. Fire the rockets! Go! 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 You will run out of fuel and just fall back to Earth. That's the stupid way to do it. Nope, can't do it that way. Instead, you need to use elliptical orbits to your advantage. So let's say that you start here on the Earth and you're trying to get to Mars. Perihelion distance, aphelion distance. Earth, Sun, Sun, Mars. If you figure out the semi-major axis for this, you can then calculate the period that it would take to basically get there but miss. Divide that number by 2, and now you have calculated how long it will take to get to Mars.